alaikum. This is a project that has been developed by Ashhad Shahid, myself, and two of my team members, Abdullah Memon and Noman Bashir. Although this project has been developed as a semester project for one of our courses, learning courses, but it demonstrates the power of geometric control as well as feedback linearization control, which is very important in terms of robotics. The topic of this project is tip balancing of AgileX Bunker with AuboRobot arm. We will see a little bit about these two bodies that we have mentioned, and then we will go into the detail of our project. So on the left, we have a robot arm, which is a 7-link robot arm. The base link is separate from the 7 links I have just mentioned. And at the top in the black, we have a gripper. Although the gripper has its own degrees of freedom, but we are not concerned about its motion in this project because this is not a project related to pick and place. So we will only talk about the links that are shown in orange and in blue. The links that are shown in blue are able to rotate around the z-axis, while the links that are shown in the orange are able to rotate around the y-axis. So the convention is the rotation axis of the orange link is the y-axis, the rotation axis of the blue links is the z-axis, and the third axis is the x-axis. On the right, we have a bunker robot which has a total of 18 wheels, 9 on one side and 9 on the other side. Although all of these wheels are able to rotate separately, but we will consider it as a differential drive for the purpose of ease of the control. So the task is that we mount this manipulator, robotic manipulator arm on top of the bunker, and the idea is that the robot arm should be able to rotate and move in a way so as to compensate for the rolling motion that the bunker will go through as it goes over a hurdle. We will see this a little in a little bit of time. On the top we have the dynamic equation of the bunker of the robot arm. The m is the mass matrix, q double dot is basically the acceleration of the robot arm, the c is Coriolis's and centripetal terms of the forces, q dot is again it's the velocity of the arm of each of the link, b is the damping term, q dot again is the velocity, g of q is the gravity torques, and on the right side of the equation we have the input torques. It's important to understand that each link has its own position as well as velocity and acceleration. One thing important to understand over here is the b term is not taken from any of the model. It is an approximation of what the term should look like. So we have a clamping limitation of rotation on the links that are able to rotate in y-axis, so as to ensure that they do not collide into the robot or other links themselves, and the z-axis joints, they remain unclamped, which means that they have a rotation from minus pi to pi. So the first controller we try is the PD with gravity compensation controller. The error function is defined as the desired location, the desired pose, which is subtracted from the actual pose. So over here the actual pose, the desired pose is dynamic, which the controller will figure out on its own depending upon the task that it has to stabilize the bunker robot when it goes under the roll, and the control law is given by minus kp into the multiplied by the error term minus kd multiplied by the velocity term and the g of q term, which will ensure that the gravitational torques are cancelled out. Over here we can see the implementation of this controller. As you can see, the bunker, as it moves over a terrain which is which has the profile of a triangle, goes under roll, and we can see that the roll velocity omega is changing, and the arm on the right side, each link is moving so as to ensure that the bunker does not go into roll. But you can see at around 2 seconds in the right side, the bunker goes into roll again even though it has stabilized. This is because on the left side, as we can see, the arm is not able to return to its home pose even after the stabilization of the bunker, but it keeps flailing about, which would induce a counter roll motion. This prompts us to incorporate another controller, which we have tried with feedback linearization controller. And as can be seen from the control law, we are explicitly cancelling all of the dynamics of the moving arm, and we incorporate an auxiliary controller, which is given by a PD controller simply. In this case, we do not need a gravity compensation term because we are already explicitly cancelling out all of the dynamics of the moving arm. Over here, we will see the implementation of feedback linearization controller for the same task on the same system. As can be seen, as the bunker goes over the terrain, which has a parabolic profile now and a total height of 0.1 meter, we can see that a large rolling motion has been induced, and on the left side we can see that the arm moves to ensure that the bunker does not tip over. Once it has stabilized the bunker, it starts going towards the home pose. So what we did is we explicitly programmed that once the rolling motion is over, the arm should return to its home pose. The PD controller was unable to achieve this task, but as can be seen that the feedback linearization controller is very effectively able to achieve both of the tasks.